Let's continue to implement the remaining part of the queue operation in interface definition. So we are going to implement how to read the data from the front of the queue. So front function, and then we can also read the data at the back of the queue. And then finally, we are going to do pop operation to remove from the front of the queue. So in testing code, when we add the data very first time, push it, so we would assert that queue front is the data just entered. Since this is the only data, this is a front as well as a back. Now we do push again, then front of the queue remains, but back of the queue is now new data, and then queue length should be 2 now. So let's develop code up to here. Implementation. So let's implement front function const. So front function, the data is in front node. The front node is pointed by p front pointer, and then data is there. That's a front function. But we need to assert that the queue is not empty. If it's empty, front function is meaningless. And then back function is the data on the back node. The node is pointed by p back pointer, and data is there. Again, for back function, the queue should not be empty. If it's empty, it's meaningless. So front and the back, reading those is pretty straightforward. So let's test up to here. Run it. All of those test conditions are done. Now let's continue to test for pop function. So at this moment we have 10 and 20 entered there. So it's called another push. Then length of the queue should be 4. Test that. And then front and the back is front remains the same. Back is 40. Now if I do pop, one data from the front is removed. So if we test queue length should be reduced by 1. Now front 10 is removed, so 20 is front. Back remains the same. So let's do one more pop. Then queue length is reduced to 2, and then front is 30, back remains. So pop function, let's implement it. Void class name pop function. So pop function, we may need to consider several cases of implementation as well. So as we did for push function, let's visualize the structure, and then let's find all possible cases of coverage. So we have a queue variable which has 2 pointers, front and then back pointers. So we have data. They are just linked together. something like this, and the last one is null, and then front pointer is pointing to the very first one, back pointer is the last one. So pop means we are going to take the first one out, which is a front. So front is always the first node. So when you remove the front node, what are possible cases? So we are going to remove a front node. So the one to be removed, what is on left hand side, what is on right hand side? Let's find all possible cases. So front one, this one will be removed. The left hand side is always a queue. And then right hand side, one possible case is some node exists on the right hand side. Another case, left hand side is queue, but right hand side could be nothing. When the case is if count length of the queue is 1, then that's the only node in the queue. So deleting the only node means the left hand side is always a queue, but right hand side is nothing. If count is greater than 1, then right hand side there should be always one node. So we need to consider two possible cases when implementing pop function. So here, if count is 1, then we do something else, we do differently. Here in design choices that you could do is count is 1, but in public interface we have a length function, so that if you change the internal implementation later, you are not going to change the length function because it's used by others, but count is used internally only. So you may choose to change the variable name count later, like CNT, something like that. So the better design approach is if you call member function, public member function length, then the internal implementation of a length is not affecting the pop function implementation. So length is 1, then that's the only node. Length is not 1, then it's more than 1. So before we do pop, so we need to then assert that queue is not empty. If queue is empty, pop is meaningless. So else part means now we have at least 2 nodes there. So if the only node is removed, then pointer to front should be reset, pointer to back should be reset. So the only node is gone. So we simply reset P front and the P back to null. However, remember that each node is dynamically created by new operation. So we are supposed to free the memory. So what we need to do is we need to free the memory pointed by the front pointer and then reset front and back pointers. That's the case when we have the only node in the queue. But if we have more than one node existing, then the operation we are going to do is as follows. So we are going to delete this one. This one means this is a front pointer. Front pointer should bypass the first node and go to the next node. That's how to remove this one. But this one is dynamically allocated, so you need to free the memory. Here, setting the bypass link means that address of the second node should be saved into p front variable. Now, where is the address of the second node? The address of the second node is here, the link member of the first node. So the operation is p front is updated by p front arrow link. P front, current P front arrow link means this value. This value is set to P front, then this value is the address of the second node. So we do bypass this way. Actually, something very similar thing we have done in infinite stack implementation. In infinite stack, we did very similar things. That is a pop operation of infinite stack. We did exactly the same thing. So here, what we need to do is P front should be updated this way to set the bypass link. However, if we do so, P front is bypassing the first node, so that's done. But we have lost the address of the first node. We need the address of first node to free the memory. So before we update the P front pointer, we need to save it so that we can use it later for freeing memory. Then once the bypass is set, then we free the memory, which is the first node at the front of the queue. Now all done, then we need to decrement the count variable. So that's a conclusion of a pop operation. Now let's test for that. Clean the screen. So what we are going to test is this operation. So we do some pop and then check front back data and then length of the queue. So let's compile the program and then let's run it. All of those tests are done. So this is the implementation of infinite queue. And then in one more last video, we will do how to do the comprehensive testing.